Hello, this is a quick example of a regular language question you might encounter on an exam. Consider the language L1. L1 is the string that contains even A's and odd B's, and our input alphabet is A and B. Is L1 regular? A general rule of thumb when looking at languages to determine if they're regular is if the language has to keep track or balance anything, then typically it is not regular. As always, there's exceptions, but we're not going to delve into that today. So is L1 regular? We're going to go and say that it is. And so we need to prove it is by designing a finite state machine that recognizes it. Okay, so here I have my starting state, Q naught. So our language is, let's write that language again. L1, the string that contains even A's and odd B's. And I spelled contains wrong, I forgot the T, just ignore that. So to start, it's always a good idea to design the specific parts separately and then merge them together after. So let's start with our even A's. Okay, so this simple machine that I designed accepts even A's. Let's test that. Let's give our input epsilon. Okay, is epsilon an accepted string? Yeah, because epsilon is 0 A's, which is even. Okay, let's give it 2 A's. 1, 2. Yeah, we get back to the accept state. Let's give it 4 A's, 6 A's, 8 A's. You know, any even number of A's is going to be accepted in this machine. What about odds? We have 1 A. Nope, we get to Q1 and we never move from there. Okay, good. So there's our even A machine. Now let's build an odd B machine. Okay, now here's our odd B machine. So if you notice, generally I'm going to have dark blue be start state and a small circle inside of another circle be our accepting state. And I'll try to be consistent with this color coding. So anyways, our next one, we have a machine that accepts only odd B's. So let's test this out with some input. Let's go with input, so 1B. Yep, 1B takes us to Q2, which is an accept state. Okay, what about 2B's? All right, what about BB, which is even? Nope, it takes us back to Q naught, the start state, which is not an accept state. Okay, and then B, 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 3B's. 3B's does take us back to the Q2, the accept state. So now we have two machines that accept the parts of our language, but our language needs to be able to accept even A's and odd B's. Right, so this isn't sufficient. We need to continue on and kind of merge them together. It's important to note early on that our language cannot have 0 B's, because 0 is not odd. So our first state, our starting state, cannot be an accepting state as well, because we cannot, the empty string is not part of our language because we always need odd B's. So at the very least, we need 1B. Okay, and so when we're designing this, we need to keep that into consideration and start with a start state that's not an accepting state, and let's start with our B's because that's what we always are going to need. Okay, so here's our machine, our two machines merged together. If you remember, our A machine started with an accepting state, right? And our B machine did not start with an accepting state. So the obvious merge would be to use our accepting state from our B machine as our starting state for our A machine. Merge those together. And let's test this. Let's see if this can accept some even odd strings. Okay, so let's start out with a B, 1B, and then no A's. Right, because we don't need any A's, but we do need at least 1B. Okay, that gets us to Q1, which is an accepting state. Let's try something like B, 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 A, 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 A. 3 B's, 4 A's. So B, B, B gets us to Q1, the accepting state, and then A, 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 A gets us back to Q1, which is an accepting state. So that is accepted. Okay, so now we need to remember the fact that W is a string that contains even A's and even B's, But because there's no specific rule, there's nothing that specifies that it needs to start with a B, so we can imply that it needs to start with anything, A or B, anything in our alphabet. So how would we do that to this finite state machine? We add a new state for our start state to get to if we get A's. Right, so now if we get A's, and I don't know if you notice this, but I do red for A for apple and B for blue. Okay, so we get A's right there, that takes us this way, but then we can never get an except state from there, so we're going to have to merge these two together back here with blues, right, with B's. B's get us, sorry, that's not, so B's get us from Q3 to Q2 and back and forth. All right, so let's look at this finite state machine and let's kind of give it some strings to see if it can pass off. Okay, so if we give it an A, B, A, which is 6 A's and 1 B, that should be accepted. Let's see if that accepts it. So A gets us to Q naught, and then B gets us to the accept state, and then A gets us back up to the accept state. So good, that one's good, but we need to test it a little bit more thoroughly. Let's start with a B, and let's do an A, and then B, A, and then B. Right, so that's a pattern of even A's and odd B's. Okay, so B gets us to Q1, A gets us back to Q1, B gets us to Q naught, and then A gets us back to Q naught, and then B gets us back to Q1. So that's accepted. So I challenge you to find a string that's not accepted by this language, by this finite state machine. So I challenge you to try to break this machine. You should always try to prove your machine's wrong, so that way you get the points on the exam. Anyways, this is just a quick example. If I made any mistakes, I apologize. If you have any questions, leave them in the comment section below, and good luck.